Dr. Mark Winterbottom is a senior research psychologist supporting the operational-based vision assessment laboratory. His most recent research focuses on US Air Force vision standards and modernizations of vision screening practices. And his title of presentation is the Stereoscopic Remote Vision System, Aerial Refueling Visual Performance. Please.
Okay, thank you. Good morning. So I'll be looking at really performance and comfort with the use of stereoscopic aerial refueling systems. So hopefully this will be an interesting application that you'll get to hear a little bit about this morning. Just a usual disclaimer here before I get started. First, just to provide a little bit of context, so I work for the Air Force School of Aerospace Medicine, and just provide a little bit of background on our laboratory. I work for the operational-based vision assessment laboratory. So we're really interested in modernizing Air Force vision screening and standards. That is testing the vision of our aircrew, our pilots, and other operators of our aircraft to make sure their vision is good enough for the very complicated tasks that they're doing. And there's kind of a general debate going on right now in a lot of countries. If you establish a particular medical standard, it's now becoming much more important for the organization to say how that is actually related to the task. So being able to say that that is an occupationally relevant medical standard that you're drawing, because that can be sometimes a very contentious issue. And we're, in our case, making sometimes career-ending decisions based on a vision test. We do end a pilot's entire career sometimes just on the basis of a single vision test. So it can be a very big deal. So this is some general capabilities of our laboratory in addition to what I'm talking about today. The biggest part of our lab is a very high resolution simulation facility, which you see here in the upper right. So we have a daylight level of luminance, daylight to nighttime, 2010 level of visual acuity. So we use that laboratory to test our aircrew or other subjects' vision under operational flight simulation conditions. We're also looking at head-mounted display performance and how visual health interacts with the use of those type of devices. We're using virtual reality as well to look at, for example, helicopter landing and whether depth perception is important in those kinds of circumstances. And then today I'll be talking about our aerial refueling work. So the Air Force now is in the process of buying the new KC-46, a new aerial refueling tanker. Several other countries have already are in the process of buying very similar tankers. So we're going from a situation which you see here on the left. So here's a boom operator, and I don't know how well you can see it, but he's got his chin in a chin rest, and he's laid out in the back in the tail end of the aircraft, looking out a window to do his refueling task and to fly the boom to do the aerial refueling. So now we're moving to this. This is the Australian KC-30. This is showing their boom enhanced vision system. So in the upper panel here are a set of 2D displays which they use to look out behind the aircraft in a wide field of view. And then this is the stereoscopic display. So they're using this window now in place of a direct view window to do the refueling task. And so that's a stereo view of the receiver, aircraft, and the boom. So it's really a much different situation. We've been using this for decades, looking straight out a window. The boom operator is now located up in the cockpit with the pilot and co-pilot, so much more comfortable for them, but there's now a lot of technology, cameras, and 3D displays in between them and the receiver aircraft, so quite different. From an aeromedical perspective, we were very concerned that whether or not our vision standards, our current policies for screening aircrew, were really applicable to this new situation. The Air Force does maintain certain minimum standards relevant to depth perception and how well your eyes maintain alignment with each other. But those are World War II era. They certainly predate the use of these kinds of displays and remote vision technology. I won't really talk very much today about what those policies are or the particular tests that we use, but just for example, the depth perception test is really not designed to screen people out. So we have 3 different stereo acuity tests. They're all very old, Titmus type circles test, and if you fail the first one, we say, okay, try this other one. That one's actually even easier and less discriminating. And if you fail that, we say, okay, try this other test. So the tests are really not designed to filter people out. They're really designed to be pretty inclusive and really only identify very gross deficiencies. So that may not be the best thing to do for this new system. There's also, as I'm sure we're going to hear a lot about this week, reasons to be concerned. There are certainly certain parts of the population that are probably likely to have difficulty using stereoscopic displays and similar technologies. I'm talking more about flat panel stereoscopic displays today, but head-mounted displays have similar issues. The Japan Air Self-Defense Force, for example, uses a head-mounted display in place of the flat panel. They probably will face very similar issues. It's a little bit different technology, but similar issues. And we know that there's maybe up to 20% of the population that could very well have difficulties. So from an aeromedical perspective, we are quite concerned about this. There's a lot of reasons why stereo displays could cause some issues for certain people. For this audience, I think you're probably all very familiar with a lot of those issues, so I won't talk a lot about those today. But one thing I did want to point out, this is actually a hyper-stereoscopic system. So this shows the bottom of a KC-30, and that's the camera bay right there. That's a very big aircraft, so they look kind of small there, but those cameras are pretty widely separated, so it's a hyper-stereo viewing condition. So that brings with it some of its own potential complications. So to study this, we built our own simulation in our laboratory. That's what you see here on the right. So similar to the picture I showed earlier, we've got a bank of 2D panoramic displays that looks out behind the simulated aircraft. And then our subject's looking here at this 3D display to do our simulated aerial refueling task. And for our simulation, we're just using a ViewSonic passive polarizing 3D stereo display. These are just standard 2D monitors. We worked very closely with the KC-46 program office, Boeing, and Flight Safety. Flight Safety is the supplier for the training system for our new tanker. To head off, I'm sure some questions later. I can't talk very much at all about the exact configuration of the cameras. It's not really an Air Force issue. It's a Boeing intellectual property proprietary issue. But we do think that our simulation was quite representative of the actual system. We actually had some boom operators come in, fly it. They were pretty happy with the simulation, said that it looked quite similar to what they saw with the actual system. So what we're particularly interested in, again, is correlating vision test scores with operationally relevant performance. So in this case, aerial refueling. Again, I'm not going to talk very much about our older standard tests. We pretty much suspected early on that those were probably not worked that well for predicting performance. So we developed our own suite of vision tests, in particular stereo acuity. This is what our stimulus looks like for the stereo acuity test. This is a threshold level stereo acuity test, so for those subjects with very good stereo acuity, we could actually measure down to single-digit arc-second level of stereo acuity. So we could pretty accurately assess their level of stereo acuity. We did a fusion range test as well to measure how well they could accommodate, basically cross and uncross their eyes before they would go diplopic or get a double image. Then we also worked with a company called Adaptive Sensory Technology to do a contrast sensitivity test. These are what the stimuli look like for the contrast sensitivity test. So much more accurate than our normal basic Snellen and acuity charts. And again, a threshold level kind of contrast sensitivity test. So those were our three main vision tests that we used to correlate performance. For experiment 1, we focused really specifically on comparing different viewing methods. So we compared the KC46 hyperstereoscopic viewing configuration, compared that to a normal stereo, and then also 2D or just a single camera view. And for a decent-sized group of subjects, but not a really large number, just to look at what the effect of stereo was. So we do get a very reliable effect of stereo. If we compare normal stereo to 2D, we do get an improvement in our aerial refueling performance. So our subjects, on average, could much more accurately and quickly fly the boom to make contact with the receiver aircraft. Then we got another increase in performance when they switched to a hyperstereoscopic view. So clearly the addition of stereo or hyperstereo is helpful for this task. Really, if you were going to pick a task where you might expect stereo to make a difference, this is probably it. You're basically maneuvering two things in depth to make contact with each other. So it is a good candidate for the use of stereo displays. But if we separate our subjects out into two groups, and we just simply separated them on the basis of above average or below average on those set of 3 tests, contrast sensitivity, stereo acuity, and fusion range, our subjects that fall into the poor vision group, they either don't benefit from the addition of the stereo, or for hyperstereo, looks like they may actually get worse. So we have some initial indication that some people probably do not cope very well with the particular hyperstereoscopic configuration we used, or that is going to be used with the KC46 tanker. So for experiment 2, we wanted to look at this a lot more closely. So we took a much larger group of subjects. We're also very interested in how well people do over a long period of time. For the refueling mission, they can be doing that for several hours at a time. So we wanted to look at what the effect of looking at the system was over a 2-hour time period. We also wanted to make sure we were basically replicating what our boom operators have to do. So there we had our subjects alternate pretty frequently between the 2D and the hyperstereo 3D display, as they would if they were actually refueling an aircraft. So we did what we call a fighter drag simulation, just repeatedly refueling like a fighter squadron on like a long mission flying over an ocean, something like that. So we had about 30 subjects. We put them through a pretty comprehensive vision screening that included the 3 tests that I mentioned earlier. And we had them do the refueling task. We're also very interested in their level of fatigue and discomfort, so we administered a questionnaire about every 10 minutes during that 2 hours to assess eye fatigue, eye strain, eye tiredness, headache throughout the 2-hour time period. So these are the results of the subjective questionnaire. So pretty much everybody was able to finish the task. We didn't get anybody that was so uncomfortable that they just quit and left the experiment. But we did get people like this that just maxed out on the discomfort ratings pretty quickly, and a couple of people that complained of diplopia throughout a significant portion of that 2-hour time period. So we did get people that were very uncomfortable doing this task. But by and large, more of our subjects had a profile that looked more like this. So most of our subjects were pretty comfortable doing this task for even as long as 2 hours. So it was more the case that most people were fairly comfortable. So what we're particularly interested in is the relationship between the vision test and how well they did on this pretty complex task using a 3D display. So these are the correlations between our 3 vision tests and our aerial refueling performance metric. So for the refueling metric, we're measuring things like how long it took them, how many connections they made throughout that 2-hour time period, whether they collided with the aircraft or rammed the boom into our simulated aircraft. We combine that into a single metric. If we correlate the vision scores with that metric, actually all three of these are very strongly related to performance with the stereoscopic remote vision system. Fusion range in particular was also very strongly correlated with ratings of discomfort and eye fatigue. So we've got potentially a set of vision tests here that we can use from an aeromedical perspective to test boom operator candidates before they actually get selected for training. One thing I just wanted to mention briefly, we did get a pretty big effect of age, which is kind of interesting. So we did not really screen people out for any particular reason to do this task. Our boom operators can be older, especially for Air Force, National Guard, or reserves. They can definitely be well over the age of 40, so we did not screen people out for age. But we did find that for our younger observers, they were much more likely to report higher levels of discomfort and fatigue. So this is the over 30 group. I don't think anybody in that group complained really at all, and that included some people that were well outside the Air Force vision standards. One guy in this group had a very large phoria, but didn't complain. So although there might have been some reasons for them to complain, they were basically fine. So that at least suggests that VA mismatch, Virgin's accommodation mismatch, is a source of discomfort when using a system like this. So just to wrap up quickly, so a couple pretty positive findings from our initial result. I think it's safe to say, at least on the aeromedical side, that there was a lot of skepticism about going from the old direct view system to using all this technology and stereoscopic displays. But we do clearly see, at least in our simulation, that stereo and probably hyperstereo for most people does improve performance. And we mostly found that most of our subjects were quite comfortable doing this, even over a pretty long viewing period. But clearly we did find a percentage of the population that we tested had a very difficult time using the hyperstereo remote vision system. Their quality of vision, their ocular alignment, their stereo depth clearly makes a difference in being able to perform this task well. For us, that's very important. Flying a boom, doing refueling, that's a very dangerous task. So all the boom operators we talked to pretty much said, oh no, they never hit the receiver aircraft with the boom. But when we talked to the pilots, a little bit different story. They get pretty irritated if it can take a long time because they're flying on fumes sometimes. They need to make contact quickly. One pilot actually told us the boom operator jammed the boom right through the canopy of an aircraft and almost impaled the guy inside. So it's a potentially very dangerous task. We want to make sure if we can identify those people ahead of time with a carefully selected set of vision tests that we can. It's also an important training issue. We'd rather not select people, spend hundreds of thousands of dollars on them in training only to have them fail out. So it'd be very cost effective if we can identify people ahead of time that just visually they're not really capable of doing this task for long periods of time. So we are planning to continue this research. Hopefully later this summer we'll kick this off. This is, as I said, potentially career-ending kinds of decisions. So we had a pretty good group of subjects, almost 30 people, but we really need a larger group to make specific recommendations on pass-fail levels of stereo acuity or fusion range to make sure we're really accurately identifying the right people to go on to training or to be kicked out. And I didn't mention earlier that for this simulation, we really assumed everything was perfectly set up. So in our simulation, the cameras are perfectly aligned, the equal contrast between the cameras, so very ideal visual conditions. For our next round of research, we'd really like to look at degraded visual conditions as well, possibly a little bit of camera misalignment. that could just occur during missions or during maintenance issues. And we suspect that people who have less than perfect ocular health may actually have even greater difficulty under those conditions. Okay, so thank you.